Last talk of the workshop, we have Mahsa Derakhshan. I hope I pronounced correctly.
Yes.
She's an assistant professor at Northeastern, and yeah, she will talk about this result. Believe for this against the online optimum.
Yes.
Instead of the offline optimum, which is a recent trend in the community. So yeah.
Everyone, thank you for attending. Okay, so as you said, I'm going to talk about the online stochastic matching problem through a computational lens.
You might have to click once. Maybe try the pointer now.
Okay.
Yeah. Okay.
So I'm mostly going to talk about these two papers. Start with the first one, then the other one is a follow-up work which is not published yet. So in the online matching problem, our goal is to find a large matching when parts of the graph are arriving online. Today, it will be vertices, but online matching has different variants. In the online stochastic matching problem, the difference is that we have additional stochastic information about the future arrivals that we can use to potentially do better. Now, as you saw in this workshop, the literature of online algorithms mostly focuses on designing algorithms with a good competitive ratio, which is with respect to the offline benchmark, a prophet who knows everything in advance and can find the best solution. But with respect to this benchmark, there are very pessimistic upper bounds for many of the online matching problems. For example, for a simple variant of vertex arrivals in bipartite matching. So the problem that I'm going to talk about today, the upper bound of half exists. But competing with this benchmark doesn't seem very fair. So to even the playing fields, we define an alternative benchmark, which is a solution found by an algorithm that has unlimited computational power, but has the same amount of information as we do about the future. So with respect to this, so the optimal solution may have a stochastic information can be found using an exponential dynamic program for most online matching, stochastic matching problems. Any questions so far? So generally feel free to interrupt me and ask any questions. This is the problem that, specific problem that we are going to discuss today. So our graph is a weighted bipartite graph. A and B are both sides, and the W is the weight of the edge. One side is offline, part B, which we may also refer to as items. They are present from the beginning. Now, part A, they are online and they arrive in a fixed order, which is known to us. Each online vertex also has a probability of arrival, which also is known. Vertex VT is the one that will arrive at time t with probability P of VT. Now, when the vertex arrives at time t, either the vertex doesn't arrive or it does. If it does, we have to make a decision about it. Do we want to match it with one of its available neighbors or leave it forever? Yes.
Is that probability the same for each vertex?
No, it's vertex specific.
So one question?
Yes.
The weights are given, like you know them.
Yes, but we can also generalize our results to variance that like weights are not given, but you have a distribution over weights also. Yeah. Today, just focus on known weights. Okay, and as I said, our goal is to find a matching with a large approximation ratio with respect to the online benchmark, and we want to design polynomial time algorithm. Approximation ratio is defined as the expected weight of the matching we find over the expected weight of the optimal solution. Let's see an example. In the right-hand side, we have our offline vertices, left are online, and then probability of arrival. The first vertex arrives, we match it to this vertex, the second one doesn't arrive. don't do anything about it. The third one, when it arrives, its only available neighbor is already taken, so nothing to do about it. And finally, this will be our matching. This actually is not the optimal online, but here there is a gap between the optimal online and optimal offline. As you can see. So let's talk about the known results before our first paper. With respect to the offline benchmark, we know that half is an upper bound and a lower bound, so that part is closed. For edge arrivals, which is not the focus of this talk, there is a gap there even with respect to the offline benchmark. Before our work, there was an algorithm with 0.5 to 6 approximation, and we also know that it's p-space hard to approximate this, to approximate it within a small constant. In the first paper, we give a 1 minus 1 over approximation. Then there's a follow-up work, which is not ours. We have this recent work, which is a 0.678. And we also have something for edge arrivals. Any questions?
So the recent work is 22 or 24?
Oh.
Yeah.
It's actually not published yet, so sorry about that. Okay. So just to go over the notations again, B are the offline parts, A online, BT is the vertex arriving at time t, and PV is the probability of vertex V arriving. Okay. All the algorithms that I'm going to talk about today are rounding, mostly they are rounding procedures. So let's start by talking about an LP and then rounding them. So XE is the probability of an edge joining the matching. We want to maximize the expected weight of the matching. So that's the objective function. Very standard constraint, which is the no vertex can be matched with probability larger than it actually appearing. Should be a fractional matching. This constraint is specific to the online benchmark. This is the reason you can round this LP better than half. So okay, let's see what it says. Consider some edge between vertex V, which is online, and a vertex U, which is offline. Okay. When can we use this edge in our matching? We can only use it if vertex V, the online vertex, actually arrives, and the offline vertex is available at that point, meaning that it's not already matched with some other online vertex. But the thing is that these two events are independent. Because when the online algorithm is making a decision about vertex U before time t, it doesn't know whether we actually will arrive or not. This is not true for the offline edge. So because of that, we can write this term as product of probability of the vertex arriving time, this whole thing, which is probability of U being available at time t. 1 minus sum of probability sum of XE's for all the edges that arrive prior to T and they're connected to vertex U. So let's first talk about this half approximation algorithm, which is with respect to the offline benchmark. And then we'll see why it doesn't work well for online. So we define this term, which is alpha of U, some offline vertex, and time t. And that's basically the probability that the vertex is matched by time t by the LP. Right? So sum of all the XE of all the edges connected to that vertex before time t. We're going to refer to this a lot. So now at time t, at time 4, this is basically going to be sum of XE of these two edges. Is it a pointer?
Supporting? Yeah, I'm not sure. Laser, yeah.
Okay, I use my fingers, it's okay.
I also tried a whole bunch of things.
Okay. So this is the half approximation algorithm with respect to the offline benchmark. When some online vertex arrives, it picks one of its neighbors randomly, such that each vertex is picked, each neighbor is picked with this probability. So the way it works is that this ensures that each vertex is actually picked with probability x of that edge between the two. Okay. Now, I'm changing the wording here to be consistent with our algorithm. It's actually not the wording used in the paper. Now, if that vertex picked by V is actually available, okay, if it's not available, you can't match it, right? But even if it's available, it will be accepted with some probability. It will not always be accepted. And this ensures that any offline vertex is always available with probability at least a half. And because each vertex is picked with probability x of the edge, it ensures that, it ensures that the algorithm will have approximation, meaning that each edge joins the matching with probability x over 2. Now let's see how the first paper tries to improve this and get better than half. So there are two things that can be improved about this algorithm when we talk about the online benchmark. The first one is that this algorithm only, if you think about it, sends on each online vertex sends only one proposal, and if it's rejected, it's over. That online vertex will not be matched anymore. And the second one is that clearly it doesn't use the crucial LP constraints because it's designed with respect to the offline benchmark. Now, the first paper with respect to the online benchmark tries to change these two things. What they do is that they design a second chance algorithm to increase the matching probability of each edge. So if the first proposal is rejected, let's say we are here, this is the online vertex. If the first proposal is rejected because it's already matched, then they are allowed to send a second proposal. In this way, they can increase the matching probability. It's not trivial because what if conditioned on that the first proposal is rejected, the second also is rejected, but to say that's not happening, they have to bound the correlation between these events to show that half can be surpassed, and they have to carefully adjust the proposal and acceptance probabilities. Okay. So now this is our first paper on this problem, which is we get 1 minus 1 over the approximation. And see what the differences are between our paper and the previous one. The first is that instead of the online vertices sending proposals, in our algorithm, the offline vertices do that. And what's the advantage? When an online vertex receives the proposal, because it can see all its proposals at the same time, it can pick the best one, right? But when an offline vertex receives proposal, it doesn't see the future proposals, so it has to reject them with some probability. So this is the first advantage of our work. The second one is that because when the offline vertices are sending proposals, they can continue sending proposals as long as they are unmatched. This is our rounding procedure, which is when some online vertex arrives, any of its neighbors send a proposal to it independently with its probability. What is this probability? Oops. So in the denominator, we have x of the edge between them. Here we have probability of the vertex arriving. And this is 1 minus that alpha that I mentioned, which you can interpret as probability that the offline vertex is available in the LP solution. Now, if the vertex arrives it receives at least one proposal, it accepts the best one. And taking the best one is important because the graph is weighted, and picking the best one ensures that we are actually getting the approximation that we want.
So to make sure, so this probability of U being available is is it like, you mean exactly that probability for this
Uh,
process?
no,
Or you
okay,
mean
so
like,
it was just interpretation. If you wanted like to be very careful, it's 1 minus that alpha term that I
Sure.
mentioned. And we can do this because of that special constraint, because it basically says that this number is smaller than this number. So which means this is actually a probability. See again what happens here. At this time, instead of this guy sending proposals, it receives proposals, say from both of them, and picks the better. Now, what are the differences between these? As I mentioned here, the offline vertex send proposals, right? And the advantage is that the online vertex can see all its options, and because of that, it doesn't have to reject any of the proposals. It doesn't have to reject proposals just to stay available. And the second thing is that we can send proposals with a higher probability because of that crucial constraint. So now, if you think about it, it's not very difficult to see that each vertex, each edge is actually proposed with probability xe of the edge. Let's see why. It's going to be proposed if the online vertex arrives and the offline vertex is available. Our algorithm is designed in a way that it never overmatches a vertex. So this number, so first of all, this to cancel out. The second thing is that because our algorithm doesn't overmatch, this term is smaller than that, so it's going to be lower bounded by xe of the edge between bt and t. So now, if say we were in a world that we could accept all the proposals, we get an exact solution, right? But we can't do that because there are collisions, right? A vertex may receive more than one proposal, has to reject some of them, and we have to deal with that. For that, we have a pair vertex analysis, meaning that we are trying to show that for any vertex, the expected weight of its matched edge in our algorithm is at least 1 minus 1 over e times the expected weight of its matched edge in the LP solution. And for simplicity, let's assume that probability of the vertex arriving is 1, because in the analysis they just cancel out. So if our graph was unweighted, this is what we wanted to prove, right? That the probability that it receives a proposal is at least 1 minus 1 over e times xe, sum of xe of its edges in the LP solution. Okay. But because our graph is weighted, we need to choose something slightly stronger, and that is that for any subset S of its neighbors, the probability that it receives at least one proposal from that subset S is at least 1 minus 1 over e of the contribution of those edges to the LP solution. Okay, and the reason that this is enough is that the vertex picks the best proposal. Picks the best proposal. That's why this is enough for the weighted case. Now let's try to prove this now. Let's first assume that the proposals that vertex V receives are independent. Okay, first of all, why can they be correlated? As I said, at any time t, the neighbors send proposals independently, but their existence can be correlated, right? Because they may have previous common neighbors, right? That makes their availability at time t correlated, right? So because of that, the proposals that an online vertex receives are not independent, potentially can be correlated, right? But for now, let's assume that they're independent and see how we can get 1 minus 1 over e. Here, what is this then? It's the probability that vertex V receives at least one proposal from set S, which is 1 minus product of probability that it doesn't receive a proposal from the edge. And we have this standard inequality, which is this term, because sum of x is at most 1, is lower bounded by 1 minus 1 over e times the contribution of those edges to the solution. Okay, so we could have this 1 minus 1 over e approximation if we knew that things are independent. How much time do I have?
You have like 10 minutes.
Okay. So, It's a But like, as I said, the proposals may not be independent, right? But we would also be happy if they were negatively correlated, because negative correlation also allows us to prove that inequality. But that's not even true. We have examples that show they can be positively correlated. To deal with this, in our first paper, we have to do some complicated stuff to show that despite having that correlation, things are still as good as being independent. Okay, but in our second paper, we come up with a very simple trick that actually makes things independent. And then we also have some extra ideas to go over, go beyond one minus one already. Okay, so now let's talk about that simple trick. So there are some adjustments to the algorithm. So in the previous algorithm, at time t, you first see whether the vertex arrives or not, then its neighbors and proposals to it. Here you see, okay, you say, forget about whether the vertex arrives or not. Let's first form the subset of proposals, and then we'll deal with it. So each of its available neighbors sends a proposal to it with the same probability, independently. So, and let's say S is the subset of these proposals, right? Now, the only vertex that actually cares about the vertex VT actually arriving or not is the best one in the set, because that's the only one that could potentially get matched with VT. Okay. So now if VT arrives, we match it with that best proposal. Okay. The reason for correlation in the previous algorithm was that now the rest of them which remain available, they are available for the same reason, right? So there is correlation with them. We want to get rid of that. So what we do is that we say, look at the subset, the rest of the vertices in S, right? And let's discard any of them independently with probability PV, which is the probability of the vertex arriving. So we are satisfying the marginals. Yeah. And things are independent now, right? Because the proposals are independent, and the existence of the vertices from this point on is also independent. Right? Yes.
By discarding, you mean they're not available to match?
Yeah, they're not matched, but they will not be available in the future.
What is UB here?
So this is the best
The best in this.
proposal, right? So the proposal that has the highest edge weight. Yeah, so this makes things independent, and that's the whole analysis for 1 minus 1 over E. Now, to go beyond 1 minus 1 over E, we cannot have independent proposals anymore. Okay, let's think about this example. You have a single vertex, a single online vertex, and all in the LP solution, somehow all the XEs turned out to be 1 over N. This example is actually possible. You can have an example that returns its LP solution. Now, if you send independent proposals, you get exactly 1 minus 1 over N. You can't get better. You have to send these proposals in a more careful way and negatively correlate. That's exactly what we do in the second paper. Okay, let me go back here. The whole thing here is forming the subset S. The rest of the algorithm is similar, but forming of that subset S is going to be in a negatively correlated way. We still want the sampling to be done in a way that the marginals are satisfied, meaning that at any time t, where the offline vertex joins the set S with probability XE of the edge between this vertex U and the available and the arriving online vertex. Okay. What we want to kind of correlate the proposals in the best way possible. Let's say f of t is the set of available neighbors to the online vertex. Okay. Let's say one of them wants to send proposal with probability 0.2, the other one wants to send proposal with probability 0.3. If you send independently, you cannot get half, right? But ideally, we want for this online vertex to get a proposal probability half. This is what we do. You have these two, they never send proposals simultaneously. One with probability 0.2, one of them sends proposal, with probability 0.3, the other one. So they are kind of perfectly correlated. Now, it is possible that the neighbors, the sum of probability of them wanting to send proposal exceeds 1. In that case, we ensure that at least one of them sends a proposal. This is what we call perfect correlation in our paper, because condition on what set F is available, this is perfect. But then this makes things correlated now. The availability of vertices in the future will be correlated. It's not independent anymore. To deal with that, we show that the availability of vertices will be negative, the negative standard dependence between them. This is the stronger notion of negative correlation. Now, there are two parts of the proof. First is to show this, and the second one is that knowing this, what would be this term? What would be a lower bound for this? Yeah.
Are you still doing the discarding thing or now?
Yes,
that's not
yes.
it?
So it's basically the same algorithm, just forming of subset S is not independently. So S is done using a different sampling.
Yeah, because I thought the goal of discarding was to make it independent, but now anyways, independence is
So
gone.
you need that to still get that kind of correlation, that the kind of negative correlation. Yeah, it's very important even for. Okay, so I'm done with this part. Now let's talk about. Okay, any questions? So let's talk about some future directions. I believe that the most important question is to understand the complexity of online stochastic matching in all these different steps. Some of them that I didn't discuss today are unweighted graphs when arrivals are IID, vertex weighted, all these different variants. And also something that's not studied very well is this the online benchmark for other Bayesian selection problems. I know that there are some works for profit inequalities, but there are not many papers on this. So it's very interesting to see what other Bayesian selection problems have been studied. Thank you.
For questions?
So have you, for instance, thought about extensions like to more general resource allocation problems, like more like combinatorial options or something beyond matchings?
No, it's been mostly matchings. But we can talk about that.
Yeah.
Yes.
So you said you can make all this work for the case when you have distributions on the edges? If you have distributions on the values instead of the values themselves?
Yes, but there's a catch. So the distribution should have constant size. For example, you can tell me that there are constant many possibilities for this vertex. It's like edge weights. So because we have
The constant or maybe polysize is also fine. I guess you need the LP should be solvable. You need, yeah,
Yes.
polysize.
All right, let's thank Mahsa again. Yeah, thank you all for joining for the workshop. It was great, I think.
Yeah, thanks a lot
Hope you
again. Yeah,
you
yeah.
also
Good time, and hopefully you enjoyed the workshop
Yeah.
as well. Thank you, guys.
also-